All right, welcome to Electrochemistry Part 3. In today's lecture, we're going to talk about voltaic cells in action. So remember, these are spontaneous electrochemical reactions that are generating an electrical current. So they allow us portable energy in the form of a battery. We're going to talk about non-spontaneous reactions and what we have to do to get those reactions to happen. That's what we're doing when we're recharging batteries. Those are called electrolytic cells. And we can predict the products of an electrolytic cell, but it depends on the conditions that we have. So we're going to look at 3 different conditions. We're going to look at molten salts, which are salts that are liquid that have no water present. We're going to predict the products of an electrolysis where I have a mixture of ions and cations. And then we're going to look at what happens in an aqueous solution. So most of our electrolysis cells are actually in an aqueous solution, and because we're supplying energy to this non-spontaneous process, we have to consider water. And so water complicates that question significantly. And then we're also going to talk a little bit about corrosion at the end and how we prevent it by galvanizing nails and things like that. So that's our objectives for today. So just to talk about energy. So in a voltaic or galvanic cell, because it's spontaneously driven, it's essentially our source for portable energy. So anytime you think about portable energy and the energy that's in a battery that you're not having to plug into a wall to an electrical outlet, that's going to be a voltaic cell, and it's driven by a spontaneous process. And so we have dry cell, we have alkaline. So these are 2 different types of batteries. We have lead acid storage, which is the battery that you have in your car if you have a traditional style car. We have rechargeable batteries. These are nickel cadmium, nickel ion batteries, lithium batteries. These are all going to be kind of rechargeable. And fuel cells, which is being used in some types of electric vehicles. And so we'll talk about those today. So the first one is this dry cell. And dry cells, it's not that they're dry, it's not very liquidy, it's kind of viscous. And these were the first batteries that were introduced back in 1866. And they had an inert graphite rod. They're 1.5 volts, so your typical 1.5 volts used to be a dry cell. Now they're alkaline cells, and so that's our Duracell and Everlast, and the batteries that we buy now are no longer dry cell. They're still 1.5 volt, but they're alkaline batteries, and they're in a basic environment, and they've kind of replaced those dry cells. And the main reason that they did away with the dry cell into the alkaline is the alkaline allows us to use these batteries in really low temperatures. I'm talking like minus 20 degrees Celsius. So that's a pretty low temperature. Lead acid storage. So these are batteries. This might look familiar. This is what you would have in your traditional car as a car type battery, is a lead acid storage battery. And these are 6 electrochemical cells in sequence. Your lead acid storage is not just one, it's actually 6 kind of batteries all in one. And the chemical reaction that takes place is lead is being oxidized, that's at your anode, is solid lead is being oxidized into lead sulfate, lead ion here, and it's releasing 2 electrons. At the cathode, I have lead 4 oxide, which is a solid, and it's picking up those electrons to form lead sulfate, which lead becomes, you're reducing the lead here from a +4 to a +2. And so that's your reduction half of that reaction. So as your battery runs, this reaction is happening, and you're converting solid lead into lead sulfate, both at the anode and also at the cathode. And so you have this buildup of lead sulfate that's happening. When the battery is getting charged, you're running this reaction in reverse, and you're basically taking lead sulfate and converting it back into lead 4 oxide and solid lead. And so when your car battery is recharging, that's what's happening. When your alternator is recharging, you're putting energy back in, you're reversing these 2 reactions. This doesn't last forever, so batteries don't last forever. And what typically happens is over time, lead sulfate initially, when it's being produced both at the anode and at the cathode, is kind of in this jelly sort of format. And it's not like a crystalline hard solid, but over time, what happens to that lead sulfate is it sits and it starts to form a really hard ionic solid. And at that point, you can't reverse the reaction. And so that's why your battery, your car battery in particular, doesn't last forever, because at some point you're not able to recharge as efficiently or recharge at all, because the solid lead sulfate that you have is no longer accessible to undergo that electrolysis. You'll notice that this is in a very acidic environment. So I have hydrogen sulfate here, which can form sulfuric acid. That's a very strong acid, so it's always going to be, hydrogen is going to be disassociated from that. When you jumpstart a battery, it used to be more of a problem, but now the way that they're making the new batteries is they're a little bit more contained, and so you don't have leaks and stuff. But if you have a leak or something in your battery, that's a really dangerous situation, because what happens is you can have this sulfuric acid can aerosolize, and so you have to be really careful, especially if you're going to jump start a car. You just want to inspect that battery just to make sure there aren't any cracks or anything like that in it. So another type of rechargeable battery that we have is a lithium-ion battery. And this works really differently because it's the motion of the lithium ions from the anode to the cathode. So the migration of these lithium ions that causes the electrons to flow, so you have an ion migrating, not just an electron. The battery is recharged by oxidizing the transition metal in the cathode. So here you have at the anode graphite with lithium ions embedded in that graphite. And at the cathode, we would have a lithium transition metal oxide. So some kind of lithium complex that has oxide and a transition metal in it. And so the lithium ion is going back and forth between these. These are about, in terms of energy, a lithium ion battery is about 3 volts. So it's about double the amount of cell potential that you would have in a sort of an alkaline or dry battery. We also have some other types of batteries that you might have heard of are nickel metal hydride. So this is the battery that's used in hybrid vehicles. It can carry more of a charge per mass. It's about 1.2 volt, but it's a lot lighter. We also have nickel cadmium batteries. So nickel cadmium batteries are also rechargeable batteries. The problem with nickel cadmium batteries, and they were kind of one of the early sort of rechargeable batteries that was being used, mostly because the reagents were fairly easy to get your hands on. So nickel cadmium battery is a rechargeable, and it has this oxidation that's happening. I have solid cadmium that's reacting in a basic environment to form cadmium hydroxide. That's a solid, and it's going to release those 2 electrons. So basically I'm going from a 0 to a +2. Cadmium is being oxidized in the presence of hydroxide. My reduction reaction is I have nickel hydroxide, and this is a solid, so nickel oxide hydroxide complex, and water plus 2 electrons is going to form nickel hydroxide plus 2 OH. So this looks like a very simple reaction, because all I need really is cadmium metal. I need nickel oxide. If I have hydroxide, if I have this in a basic environment, it's going to form this solid here. And then I just let my spontaneous reaction happen. This would be my oxidation happen at the anode. This would be the cathode. I can recharge this by driving the reaction in the reverse. At the anode, I would have a buildup of cadmium hydroxide. At the cathode, I would have a buildup of this nickel hydroxide. If I apply a current to it, an electrical current to it, it's just going to reverse both of these reactions. And so that's what a rechargeable battery does, is you plug it in, you run an electrical current through it. Now you have an electrolytic cell where I'm reversing spontaneous reaction, allowing it to go in the reverse direction. The problem with these is that if there's no stoppage, because if you think about, I plug this battery in and I start to let it go through the non-spontaneous process, I'm basically driving that reaction by adding an outside electrical current to it. I have no stop measure, so I don't know when that reaction needs to stop. And so one of the problems with these nickel cadmium batteries, there's a couple of problems with it. One is when you're recharging them, it doesn't stop automatically, and so it'll just keep going, and it creates more unwanted products well, it's going to run out of this, it's going to run out of this, and it's going to keep going because I'm supplying energy. So a lot of other side reactions can happen, and these will actually explode if they're over recharged. They'll catch on fire and explode. And so nickel cadmium batteries were not very good. They were replaced by the nickel metal hydrides, which we talked about. And these are nickel metal hydride. These are also rechargeable, and these are what you're going to find in your hybrid vehicles. So hybrid vehicles are going to have this nickel metal hydride type of battery in it. The oxidation that's happening is I have some metal hydride plus hydroxide, so I'm in a basic environment. I'm going to form the solid metal and water. So this is a very clean reaction. And then in my reduction half, I'm going to have nickel oxide hydroxide. This looks familiar, right? Plus water. I'm going to have the same reaction that happens up here. I'm going to form nickel hydroxide solid plus hydroxide ion. So this is important because my oxidation step is going to be different. And so that allows us to be a little bit of a safer reaction when you have the reverse happening. My E cell potential for this is 1.2 volts, which is the same as up here. This is 1.2 volts. This is a much lighter system, and that allows you to use it in a hybrid scenario. And one of the things that happens is when you have a hybrid car and you hit the brake, the electronic motor, it absorbs that energy from the braking and uses that to recharge the batteries as well. So hybrid vehicles are pretty fascinating. I don't want to talk too much. Let's talk about fuel cells. So we could go on and on and on and on about batteries. And I'm not even really sure what kind of batteries are used in Teslas. That would be an interesting thing to look at. Is it a nickel metal hydride battery, or is it a different kind of battery now? So fuel cells look like this, and a fuel cell, you have to have a continuous supply of hydrogen and a continuous supply of oxygen, and so that's what makes fuel cells a little less adaptable to different types of environments, because it's not like you're going to have a hydrogen tank and an oxygen tank hanging around. On the oxidation half, I have hydrogen gas that's producing water. On the reduction half, I have oxygen gas that's producing hydroxide ions. So I'm having a basic environment. You'll notice that they're not separated. So the anode and the cathode are together in the same system. And then that's going to drive this electrical current here. So I don't have a salt bridge. I don't have any salts. I have pure water in solution. The only ions I have in solution are hydrogen ion and hydroxide ion. So these batteries are self-contained. I don't have a separate anode or cathode, but they need constantly replenished reagents. But the nice thing about these fuel cells is the product of a fuel cell is water or hydroxide ion. So it's really nice and safe for the environment. Okay, so when we charge a battery, we're really undergoing electrolysis. And electrolysis is when you have a non-spontaneous reaction and you're forcing that reaction to happen. So batteries would always be a spontaneous reaction. The recharging of those batteries is what we call electrolysis. I'm adding an electrical current to drive a non-spontaneous reaction. Unlike a voltaic cell, which is a spontaneous reaction, I need an electrical current through that. So this is what we would use for fuel cells, like we just shown, recharging batteries. And another important use for this is metal plating. So if I do silver plating or copper plating with another metal, I'm going to have a system set up that's electrolysis, and I'm going to run an electrical current through that and actually predict how much of the metal is going to be plated. And we'll do some of those problems in our Zoom meeting together. All right, so electrolysis, I can have three different scenarios for an electrolysis. I can have a simple one. This is going to be if I have pure molten salts. So this means I have salts, ionic compounds in the liquid state, no water present. So these are not aqueous solutions, these are molten. So I've added enough heat to move that salt from the solid phase to the liquid phase. If I think about this, let's say I have sodium chloride. Let's take sodium chloride. What is going to be oxidized or reduced? So I'm going to run an electrical current through this molten salt, and I want to know what's going to happen is what's going to be oxidized and what's going to be reduced. So remember, oxidation is loss of electrons. Reduction is gain. If I have a molten salt, there's already been a transfer of electrons when I created that salt. So this would be sodium ions in the liquid phase and chlorine ions in the liquid phase. So only one thing can happen to each of these. So oxidation is loss of electrons. Sodium can't lose any more electrons because it's already lost an electron. So sodium can't undergo oxidation. However, chlorine can. So chlorine has this extra electron here. So in the oxidation half, this is going to be my anion is going to undergo oxidation. On the reduction half, my cation is going to undergo reduction. And so that's the only thing that can happen in a pure molten salt. Your cation is going to never undergo oxidation because it doesn't have any more electrons to lose. Your anion isn't going to pick up any more electrons. So this is the simplest one because you can predict based on the charge of the ions that are in your salt which is going to undergo reduction and which is going to undergo oxidation. So if I were to write my oxidation half out that's happening at the anode, it would look like this. So that would be my oxidation half, my reduction half at the cathode, and these are all going to be in liquid because these are molten. So no water, no aqueous, nothing like that. This is pure molten. If I have water in here, we'll talk about that in a minute, that complicates everything. But if I just have a pure molten salt, this is the simplest one. Your anion's always going to be oxidized, your cation's always going to be reduced. My second scenario in an electrolytic cell could be a mixture of cations and anions. And which one is going to be more easily reduced or oxidized. So in a mixture, and we'll say this is molten, so I don't have any aqueous, no water, molten ions, I'm going to find what's happening at the anode and what's happening at the cathode. So if I have a mixture of cations and anions, now I know that anions are always going to be oxidized, cations are always going to be reduced, but if I have a mixture, one is going to be preferentially reduced over all the other cations that are in that solution. And one anion is going to be preferentially oxidized over all the other anions in solution. So this is going to be whichever one is most easily reduced. That means it has a more positive electropotential. I'm going to look at that table. And this is going to be more easily oxidized, meaning it has a more negative electron potential. So I'm just going to look at the table, and that's going to allow me to determine that. So let's say I have a mixture of aluminum bromide, magnesium bromide in a mixture. And I want to know what is being reduced and what is going to be oxidized. In this scenario, I'm going to write out all my ions. So I have aluminum ion, I have magnesium ion, these are my cations, and I only have one anion, and that's bromine. So bromine is going to absolutely undergo oxidation because that's the only anion I have. So I know that this is going to be my oxidation half at the anode. And now I'm going to look between these two, which one of these is going to be preferentially reduced. I'm going to compare my values. So if I look up in the table, what I'm going to find is I'm going to find a value for aluminum to go to a solid aluminum. I'm going to find a value for magnesium to go to solid magnesium. I'm going to use these values to compare. So my half cells here, this is negative 1.66 volts, and this is negative 2.37 volts. So neither one of them is particularly great, but this is going to be less negative, so it's going to be more easily reduced. If both of these are positive values, then I'm going to look for the value that's more positive. If they're both negative, I'm going to look for the value that's less negative. So it's getting closer and closer to zero. So this is going to be the reduction reaction that happened at the cathode. And magnesium ion is just going to stay in. So it's going to be a spectator ion. It's not going to be involved in this reaction at all. All right, if I have the third scenario where I have an aqueous mixture, and remember these are all electrolytic cells, now I have to consider water. Because water can undergo oxidation and water can also undergo reduction. And so oxidation for water looks like this. I'm going to form an acidic environment at that anode, and I'm going to produce oxygen gas. So if I have an electrolytic cell and I just have water in there, I run a current through it, I'm going to see bubbling at the anode. That bubbling is going to be oxygen. What's going to happen at the cathode? The reduction of water. So the reduction of water starts with water, obviously. Since this is a reduction, I'm adding electrons in as a reactant. I'm going to form hydrogen gas at the cathode and hydroxide ion. So a couple of things to point out. This is going to make it a basic environment at the cathode, and I'm going to generate hydrogen gas. So if I'm not sure what's happening at the anode or cathode, I could take a pH check, because if I'm oxidizing water and I don't realize it, I'm going to have an acidic pH in the anode. If I'm reducing water at the cathode, I'm going to have a basic pH. And I'm going to see bubbling at both of them. So that bubbling is a giveaway. I have an aqueous solution of lithium iodide, and I'm going to run it through an electrolytic cell, and I want to find out what's happening at the anode and what's happening at the cathode. So I can't just say, oh, well, I have lithium ion and I have iodide ions. I can predict basically what's going to happen based on the charge of these. I'm in an aqueous solution. I also have the ability for these two things to happen. I'm going to compare my half cell potentials for these, and I'm going to give you this is negative 0.41 volts. So these values are going to be fixed for the reduction and oxidation of water. And then I'm going to look at my values for these, and I'm going to compare. So oxidation, I have water as a potential, and I also have iodine. So if I look up iodine on my table, I'm going to find this. I have a pretty high half cell potential here. This would be my reaction that's happening. On this side, I have lithium ion at the reduction, and my half cell potential here is minus 304 volts. So the oxidation, to oxidize, this is going to be at the bottom of that table. So the more negative value, that's going to be the half reaction that's happening. So I have a positive 0.82 and a positive 0.54. So neither one of these is negative. I'm also going to look at least positive. So the smallest of those two values, which happens to be iodine. So this is going to be happening exclusively at the anode because my half cell potential is smaller than it is up here. So this is happening at the anode. I don't have to worry about water, and I shouldn't see any bubbling at the anode. At my reduction, now I'm going to look for the more positive value. So I have a negative 0.41 and a negative 3.04. Normally what I would be looking for is the more positive. I'm also going to look for the least negative, right? The one that's higher up on that list. More positive, least negative. That's going to be water, because this is a negative 0.41. This is a negative 3.04. So this is what's happening at my cathode. So I should see bubbling happening at the cathode. And so I'm really not undergoing electrolysis of lithium iodide. Iodide's undergoing oxidation, but water is undergoing reduction, and lithium is just a spectator ion. And I know that because I looked up these values and I compared them to the electrolysis of water. So anytime you have an aqueous solution and you want to find out what's happening, you have to do that. And we'll do some of these problems together in our Zoom meeting. Just to reiterate, things that are higher up on this list are going to undergo reduction. Things that are lower on this list are going to undergo oxidation. And water is on this list. Water is here, and water is here. Kind of have it marked out here. And you'll notice that these values are slightly different than the values that I gave you. These are the values under standard conditions. These are the actual values that you're going to see that are going to affect the water. So when we think about the electrolysis of water, these are going to be the values that we use in that comparison, as opposed to the values that are on the table. So here I have electrolysis of a molten salt. And so you can see that at the anode, what's happening is the anion is losing electrons. At the cathode, the cation is gaining electrons. If I just have an aqueous salt solution, it's going to depend. And here, instead of lithium iodide, I have sodium iodide. But the fact that I start to see bubbles here at the cathode tells me that I have water that's undergoing electrolysis, as opposed to the sodium ion here, because sodium ion wouldn't be generating these bubbles. And then if I were able to take the pH of this, I would find that it's going to be really basic. Right, the last thing I want to cover is just to talk about iron and what's happening when iron rusts. If I have iron metal, and let's say I have a chink in that. So what you'll notice is usually if you have metal and it starts to rust, it usually rusts at a point where you have a scratch or something like that that has kind of broken the surface, because usually this is painted or it has a coating on it. And once I get kind of like a scratch on that piece of metal, that's where I'm going to have some issues coming in to play. This will happen anyway, but this is really going to significantly speed up that process. So what's happening is that iron metal is going to undergo oxidation to form iron ion, which doesn't have any of the metal properties that we think of, plus electrons. And those electrons are going to be donated, right? Because this is 1/2 of a redox reaction. So if this is losing electrons, something else has to pick up electrons. The electrons can travel through the metal because metal is really good at conducting electricity. So my electron will travel through the metal, and if there's water present, what it's going to do is it's going to, in air, it will transfer those electrons, especially if I have an acidic environment, to form water. So if I have oxygen present, I'm going to undergo oxidation. My iron is going to donate 2 electrons to the oxygen, which is going to, if I have hydrogen, if I have anything that's even remotely acidic, I'm going to form water. Now what water does is water will also react with the iron. If I have iron 2+, this can go on in the presence of oxygen to form iron 3+, which gets deposited as rust. So this is rust here. Rust is iron 3+, so it's actually iron 3 oxide. And there's going to be some water complex in there, and it's a solid. First off, iron gets oxidized to iron 2+, then in the presence of oxygen, it's also going to form water. In the presence of oxygen, the product of this is going to go through a further oxidation process to form iron Fe3+. That's going to deposit on my metal and start forming rust. And so rust actually forms on top of okay metal, and then as this grows, the metal that's underneath here eventually turns into iron oxide as well. If you think about it, this whole thing gets speeded up when you have salt present. So this would be if I had a big water droplet. If I had a water droplet on there, this is going to happen. I'm producing water, so I'm making more water here. If I have a salt, this is going to speed up the process significantly because it allows this electron to be transferred even quicker. So dissolved salts in water conduct electricity really well. They also conduct electricity really well when you have this rusting going on. A lot of times what will happen is if they want iron not to be able to undergo corrosion, you might coat it with something. So oftentimes aluminum metal is used to coat iron because aluminum will preferentially undergo oxidation over iron because it's lower in the list. So I see aluminum here and iron is here. And so if aluminum is present, then, let me move this up. If aluminum is present, it's going to preferentially undergo oxidation over iron because it's lower in this list. And so oftentimes aluminum coating metal will help the metal from rusting because the aluminum will undergo oxidation over iron, and that'll be your oxidation house. So instead of forming iron 3 oxide, what you form is aluminum oxide, and aluminum oxide sits down on the metal as well, and then that protects it from further rusting as well. So you have kind of like a double good that's happening. If you coat it with aluminum or you have aluminum nearby, or if you have aluminum that's even touching this metal somewhere, as long as they are in contact, the aluminum will be oxidized over the iron, and then it's going to produce aluminum oxide, and that'll get deposited on this metal, and that'll also keep it from being corroded. So that's when we galvanize steel, metal. Galvanized is usually using zinc, molten zinc, and so you take the nail is dipped into molten zinc so it looks really shiny. You don't have to fully coat it as long as the two metals are touching, but it's more easily oxidized, so the zinc will corrode first. as opposed to the metal that's making up, or the steel that's making up that nail. So that's what a galvanized nail is it just, it has, usually zinc is the coating that's on there that allows that to oxidize the zinc over the steel of the metal. So that ends electrochemistry, and I hope to see you guys in our Zoom meeting.